Welcome to Mr. Frolic's physics classes. In this video, we will discuss conservation of linear momentum. Hello there. Let's start today's lecture talk about the total momentum of a system of particles. So, if I have a system of particles, say 1, 2, and 3. I'm going to stick with just 3. So particle 1 with a momentum p1, then particle 2 with a momentum p2, and perhaps particle 3 with a momentum p3. The total momentum of the system, p total, is going to be the vector addition of the momenta of all of the particles of the system. On this example, p1 plus p2 plus p3. Okay? In a system with a number n particles, a large number of particles going up to n, I could say that p total would be the sum of I going from 1 to n of the pi particles. And notice that that would be a vector addition. The next important concept for us to address is the concept of system and internal or external forces. And to help us better understand this concept, I'm using here now a picture from Hewitt's book, The Orange and the Apple. So on the first system, you can see that the apple is not part of my system. The dashed line that determines the system. So on the first picture, only the orange is part of the system. So the agent of the force is outside of the system, and the object is inside of the system. The line that connects the two crosses the boundary of the system. The force that the apple exerts on the orange, in that case, is an external force. On the second picture, the one down below, the orange and the apple are now both considered to be part of the system. And then we can see that both agent and object belong to the system. Or that the line that connects the two does not cross the boundaries of the system. And then the force that the apple exerts on the orange is an internal force. Okay? So an external force is when the agent of the force does not belong to the system, or when the line that connects agent and object on a system schema crosses the boundaries of the system. And an internal force is when both belong to the system. Notice that that concept is a relative concept. Nothing is, absolutely speaking, an external force or internal force. It always depends on what you call your system. Now, let's see why that concept of internal and external force becomes important for us. Back to my system of 3 particles with momenta p1, p2, and p3. Let's say that I also had some external agent, I'm going to call hand 1, acting on particle 1, F hand 1 act on particle 1, and perhaps an F hand 2 acting on particle 2, plus the mutual action-reaction forces between all of those particles. The net force on the total system, oops, wrong color. The net force on the total system is going to be the summation of all of these forces. So that's going to be, for example, force of the hand on 1 plus force of another hand on 2 plus force of 1 on 2 plus force of 1 on 3 plus force of 2 on 3 plus now force of 2 in 1 plus force of 3 in 1 plus force of 3 in 2. On my simplified example of 3 particles, these would be the force acting on my system. Notice that these 2 forces here are my external forces. Some agent from outside of the system is exerting these 2 forces, and then they are going to be external. And these forces here are internal forces. They are the forces that one part of the system is exerting on another part of the same system. Then I can rewrite my net force total this way here. That the total net force on the system equals the net external forces plus the net internal forces. The problem is, the net internal forces, when I add them, F1 and 2 is equal and opposite to F21. So when I add the 2, they zero out. Same thing with F13 and F31 and F23 and F32. So what I have is that the net force of the internal forces is going to add up to 0. Those always will cancel out. And the net total force on the system is going to actually be given by just the summation of the net external forces on my system. Let's now talk about a system, Newton's second law, and when the system is isolated. So first, an isolated system is a system where the net external forces act on it is 0. Okay, so an isolated system, in our view, is a system where the net force on it is 0. Now, why this becomes important? Let's remember that according to Newton's second law, net force is the time derivative of momentum. Is going to be dp dt. But if the net force is 0, then the derivative of momentum over time is 0. But that then means that the momentum total of the system must remain constant. Okay? So what we have at the end of the day is this here. If my system is isolated, the total momentum must remain constant. We usually can write this here as actually saying that the total momentum after some event, final, must be equal to the total momentum before some event. Okay? And this here is the way we're going to actually use this principle. And this is basically known as conservation of momentum. And the whole idea is that if the system is isolated, which means the net external force on the system is 0, the total momentum of the system will remain constant. So we have that the conservation of momentum principle tells us that if the net force on a system is 0, the momentum total will remain constant. This principle, which looks very simple at first, is actually one of the most generic, most powerful principles of conservation that we have in physics. It's applicable in collisions, in relativity, in quantum mechanics, everywhere this principle is applicable. And what we'll do now is see a couple examples and situations so we can better understand how this works. Let's consider a system of two particles, 1 and 2. So here is 1 with an initial momentum p1 and particle 2 with initial momentum p2. They will somehow get closer together, suffer some kind of interaction in which we don't really know exactly what's happening. And after this interaction, particle 1 moves out, moves out of there with a final momentum p1 final, while particle 2 moves out here with a final momentum p2 final. Let's also assume that the system is isolated, so the net external force on it is 0. The total momentum final is going to be equal to the total momentum initial, okay? Because of the conservation of momentum. But the total momentum final is going to be P1 final plus P2 final. Equals to the total momentum initial is going to be P1 initial plus P2 initial. Now, I can rewrite this equation sending everything that depends on 2 to the left-hand side and everything that depends on 1 to the right-hand side. And then my equation can be rewritten as P2 final minus P2 initial equals to P1 initial minus P1 final. But the left-hand side of this equation is actually the change in momentum of particle 1. And the right-hand side of this equation is the negative change in momentum of particle 2. So I can go ahead and write that delta P1 equals negative delta P2. And this here is another important equation or important concept for us. If my system is isolated and one part of the system gains momentum in one direction, delta P1, the rest of the system must gain momentum on the opposite direction, equal and opposite change in momentum. So the total momentum of the system will not change, will remain the same. We can also still move forward here because delta P1 is the impulse on particle 1. And delta P2 is the impulse acting on particle 2. But impulse is force, so that's going to be force 2(1) multiplied by time equals to impulse on particle 2 is force 1(2) multiplied by time. And the time is the time of the mutual interaction, so that can cancel out. And what we have at the end is F21 equals negative F12. And this is an expression for Newton's third law, the action-reaction pair of forces. So we can also, if we understand that momentum and conservation of momentum are more fundamental principles than Newton's laws, we can see that Newton's third law is a direct consequence of momentum.